Welcome to the fourth lecture. We have already seen that the Z1 by 4Z2, an important ratio. Z1 is the impedance of the series elements, or Z1 by 2, the series elements, and Z2 is the shunt element, that impedance. That ratio in the pass band it should be in this range, and in stop band it should be in this range. You know, impedance is always, for a reactive elements, is a function of frequency. So, in pass band we need to enforce this, stop band we need to enforce this. So, this boils down to this. If I plot Z1 by 4 Z2, I have 2 points 0 and 1. So, any Z1 by 4 Z2 greater than 0 is a stop band. So, this entire thing up to infinity is stop band. So, let me write this is stop. Also Z1 by 4 Z2 less than minus 1 is stop band. So, this is also stop band. So, I have only this zone, this is my pass band. Okay. So, now we got a filter, we know that how I will have to choose the Z1 and Z2. So, I get pass band, but another thing remains, that we have found out that in pass band alpha is 0 and in stop band alpha is not 0, but what is its value, that we have not found. So, we will have to find the value of alpha in the stop band. Also, we will find what is the value of beta in the stop band, because beta is phase constant. So, as the wave moves per unit length, how much phase changes, that also is a curiosity. And in pass band we have seen that alpha is equal to 0, but what happens to beta here, how beta changes in pass band. So, that we will now see, that we have already seen, because everything is embodied here, tan hyperbolic square gamma, or let me start in a new, tan hyperbolic gamma square is Z1 square plus 4 Z1 Z2 by Z1 plus 2 Z2 square. We have already seen this number, I think this. You see, already we have derived this, that tan gamma is here. Now, we will try to see that under those stop band per band condition, that means under the Z1 by 4 Z2, that range, what happens to alpha, what happens to beta, both in stop band and pass band. So, this is the number. Now, let us do a bit manipulation, and from this we can find out that cos gamma, these are all manipulations, so that the thing become a bit simplified. Cos gamma, from tan square gamma I can always find cos gamma, that will be 1 plus Z1 by 2 Z2, but we want to express it in terms of Z1 by 4 Z2, because our condition is this condition is Z1 by 4 Z2. So, a bit more manipulation, and we get that sin hyperbolic gamma by 2 is this number Z1 by 4 Z2. So, from here I came here, from here I came here. So, now sin hyperbolic gamma. So, here you put this sin hyperbolic gamma means alpha plus j beta by 2 is equal to root over Z1 by 4 Z2. Let me expand now. Sin hyperbolic alpha by 2 cos beta by 2 plus j cos hyperbolic alpha by 2 sin beta by 2 is this. Good. Now, I now designate the two bands, because I have two stop bands. Every time, instead of saying that, let me call this is my stop band 1 and this is my stop band 2. I have only one pass band, so no problem. So, I have got this. Let me see one by one. In stop band 1, in stop band 1, what is the definition of stop band 1? What is stop band 1? Z1 by 4 Z2 is greater than 0. So, Z1 by 4 Z2 greater than 0 and real. So, this is greater than 0 and real. So, can I say that if this is real, this equal to this and this is 0. So, my conditions are that this implies that sin hyperbolic alpha by 2 cos beta by 2 is equal to root over Z1 by 4 Z2. This is 1, and cos hyperbolic alpha by 2 sin beta by 2 is equal to 0, 2. So, these two conditions. Now, from 2, if this is there, we know that cos hyperbolic alpha cannot be 0. So, sin beta by 2 should be 0. And what is sin beta by 2 0? I know that beta then becomes 2n pi, where n is an integer. And from, so beta value I know. So, what is cos beta by 2 now? Cos beta by 2 is plus minus 1. So, let me write what is cos beta by 2, that will be minus 1 whole to the power n. So, putting this into, putting this value to 1, that will say that alpha is 2 into minus 1 whole to the power n sin hyperbolic Z1 by 4 Z2. So, I got the non-zero alpha value in the stop band 1. Now, let us see the stop band 2. Stop band 2. What is stop band 2? This is my stop band 2. That means Z1 by 4 Z2 is less than minus 1. So, stop band 2 Z1 by 4 Z2 is less than minus 1. So, this is imaginary, this root over Z1 by 4 Z2 is pure imaginary. So, let me see this quantity. So, this is pure imaginary. So, this should go to 0 and this should be equal to this. So, I can write sin hyperbolic alpha by 2 cos beta by 2 is equal to 0. Let me call that earlier I 1 2 said, so 3 and j cos hyperbolic alpha by 2 sin beta by 2 is equal to root over z1 by 4 z2. This let me call 4. Okay. So, this 3 implies what? That we know that if sin hyperbolic alpha by 2, that cannot be 0 here. So, cos beta by 2 is 0, that means beta is 2n minus 1 pi, n belongs to integer. So, if that is the case, what is the value of sin beta by 2? Sin beta by 2 we know that it will be 1. So, j of this is this. So, can I say that j, so now putting it here, j, putting this value here, j cos hyperbolic alpha by 2 is plus minus root over z1 by 4 z2. So, that becomes alpha is equal to 2 cos hyperbolic root over z1 by 4 z2. So, this is the value of alpha in passband 2. Okay. Now, we see what happens to passband. Passband we know alpha is 0, that we already seen, but what happens to beta? So, you see this again, that alpha is 0. So, cos hyperbolic alpha, that this term become 1. So, we have this term only. So, j sin beta by 2 is equal to root over z1 by 4 z2. So, sin beta by 2 is z1 by 4 z2 magnitude. So, I know what is beta in passband. Beta is 2 sin inverse z1 by 4 z2. So, in passband alpha is this, beta is this. In various stop bands I have. So, once we have this, now let us design a prototype filter. So, let us take, again I am taking T network, you can also take a pi network. So, for passband we know that the Z1 and Z2 should be opposite sign. Let us take the Z1 is inductive, that means the picture will be that I have inductance here, capacitance here, and again inductance here. Let us call this L by 2, this is L by 2, this is C. So, Z1 is what? Z omega L, Z2 is what? 1 by j omega c, and what is the that important number z1 by 4 z2? This will be minus omega square. If you just put this omega square LC by 4, in passband we know this number is, so passband is where this number is between minus 1 and 0. Okay. So, you can write that 1 is greater than this, greater than 0. So, you can write 1 from here, you can follow that 1 is greater than 4 pi square f square L C by 4 greater than 0. Omega is 2 pi f. So, I have written that, or 1 by pi square L C is greater than f square greater than 0. Now, this whole thing I can name as what? Fc. So Fc is what? Fc is 1 by pi root over Lc. This is Fc square. So Fc is this. All of you know this for an prototype. So what type of filter is this? You see that in passband, my passband extends from Fc 0 to Fc. So the frequencies from 0 to Fc are unattenuated, and over Fc it is suppressed or starts attenuating. So this is a low pass filter. If instead of this I had interchanged this arm capacitance, this arm inductance, I could have a high pass filter. All those you know that then we can have band pass, low pass. But what I did from image impedance concept, I have brought you here. Let me finish now that what happens when we have seen that alpha is 0 in pass band. So between 0 to F to Fc, the alpha is 0, and what is beta? We have already derived. You see your expressions. I can write it as 2 sin inverse root over Z1 by 4 Z2. I know now Z1 for Z2 values. So this becomes 2 sin inverse F by Fc. Very good. So I can draw that versus F. I can plot alpha. Acha. So before plotting, let me see the stop band, that what happens when F is greater than Fc. F and F is greater than Fc, Z1 by 4 Z2 is minus omega square Lc by 4. So you put it, in our case this. So this is F is greater than Fc. We are at which stop band? Stop band 2. If you see that you will be here because of this minus omega square Lc. So actually we are Z1 minus 4 Z2 minus omega square Lc. So we are in this part, and in this part we know that what is alpha? Alpha will be 2 cos hyperbolic inverse Z1 by 4 Z2, and that is 2 cos hyperbolic inverse F by Fc. So now you can plot alpha, that there will be an Fc. So up to this Fc, alpha is 0, this is your pass band, this is 0, but then after that it will have this type of variation, cos hyperbolic F by Fc. So that is like this. So alpha is rising here with a cos hyperbolic inverse variation. Now what happens to beta? What happens to beta? We have seen in pass band, where is beta? We have already seen, derived that in pass band beta is 2 sin inverse root over Z1 by 4 Z2. So and in stop band 2, beta will be 2n minus 1 pi. So you can take that beta is simply pi. So, if I plot Fc, so these two sine inverse this variation, so this will be something like this, and then it will stay at pi. This is beta, this is your pi 0. So, this will be the beta variation. What does that mean? Beta variation means, you see that if my baseband signal or if my RF signal that has a frequency spread, that means instead of a single tone, if I have a multi-tone things, a band of frequencies present in my voice, and suppose it is getting transmitted, if you put this filter, there will be dispersion, because this is not a linear function of frequency. So, various frequency components will be reaching the transmission thing, but since the length of the filters are small, it is not a problem. But if you go to higher in frequency, suppose you cross gigahertz range, then even this is significant and you will start having dispersion, etc. So, you need to design it from a microwave filter viewpoint. This is the problem of this low frequency filter design. And what is Z naught? Also another important point. This we have seen alpha beta, but now we will have to see what happens to Z naught, the characteristic impedance, because our whole impedance matching is dependent on that. We said that the filter is terminated by Z naught, filter is both in the source and load side. But what is the Z naught value? So, we have already seen that Z naught is Z1 square plus 4 Z1 Z2 by 2. So, what is this? This is, if you put those values, that Z1 is equal to j omega L and Z2 is equal to 1 by j omega C, you will see that it is L by C into 1 minus F by Fc square. Z naught is real in pass band, that we have already seen from that theorem. So, 0 to F to Fc. Now, at F is equal to 0, what is Z naught? You see from this expression, 1 minus, it is root over L by C, and that generally this filter design people, RF filter design, they call it K, a constant. You see L by C is a constant and Z naught here is independent of frequency, but that is only at DC, but at any other frequency, even in pass band, Z naught is changing. As we are increasing F, as F is increased, Z naught, you see, is getting decreased. If you are increasing, this part is increasing, so the total Z naught is decreasing, and at F is equal to Fc, what happens to Z naught? F is equal to Fc, Z naught is 0. So, I know the variation, so I can plot it, and also let me complete that. This is in pass band. In stop band, what will be Z? That means when F is greater than Fc, Z naught will be J K, this constant, into F by Fc whole square minus 1. Just put that in this expression. For F minus, when F is greater than Fc, you will have to bring this J out, and from here you get at F greater than Fc, Z naught is this. So, if we see the plot, this plot will be, suppose I am plotting Z naught in the x axis, F here, there will be obviously a Fc here. So, we will see the graph as So, this you see that this is your stop pass band. So, it is starting from a value of k, gradually decreasing to 0 and then increasing. So, it is a dangerous thing. You see at FC it is very good resonator, it is a good filter, it has good output, etc. But in other places it has a characteristic impedance which is not a constant value k. So, you will have the load impedance and source impedance chosen according to this characteristic impedance of the filter. So, at that only at one frequency it is matching, all other there is mismatch. So, there will be some power loss due to reflection in the circuit. This is a problem of these constant K filters, low pass filters. So, what they do, they try to improve this impedance matching. That means, instead of this graph so peaky, they try to flatten it, that is by M derived sections. They can flatten it to very good amount, but you need some extra hardware for that. So, this is the problem. So, what we will do, we will see that if I try to replicate this design to microwave filters, I will have problem due to this. I can have M derived, etc., that may solve the problem, but then it is bulky. What we will see, that you can design the whole thing completely from a different standpoint, that is called insertion loss viewpoint, insertion loss filter design, and all modern microwave filter designs are based on this. But I introduce this concept because in BTech sometimes this is, though this is part of BTech syllabus, in our present day this is not taught with so emphasis, but this has impedance, image impedance concept, characteristic impedance concept, all comes from here, which later we use for transmission line and other things. So, unless and until this impedance part is clear, propagation constant part is clear, later understanding the microwave filter designs, microwave amplifiers, that will become problem. That is why I took so much classes extra to revise this. But before completing, I say that I have always taken T section, you can also take an pi section. So, if we take a pi section, just what happens, let me see, this constant K filter, pi section. So, my filter will be like this. Again I decide this is L. So, this is L and these two I take C by 2, this is a symmetrical pi filter. So, its Z0 expression, if you now derive, it will be plot it, f, here you plot Z0 pi, actually that time I have said Z0, you can call it Z0 T section also, Z0 pi, that will be mark FC. So, this part actually here also, please note that up to this part, this is pass band, this is real, and this is the reactance part, because it is pure imaginary. But in the same graph, since we are showing, we should say that this portion is reactive, this portion is real or resistive, and here this portion is reactive, this portion is real, this is in pass band. So, you see here in the T section it was coming like this, in pi section it is increasing like this, and you can find out that when f is greater than f c, this z naught that is given by from here, just when f is greater than f c. So, L by c into 1 by root over f by f c whole square minus 1. You just take j out, that becomes this. So, other alpha betas are same, but this characteristic impedance of a pi section is different from characteristic impedance of a T section. Okay. So, actually you know that if we change this L and C, then we get high pass filter, then we can put cascade of a low pass filter with high pass filter, you get band pass filter, or in one arm instead of a single L, we can take a series of L and C. Here also we can take a series of L and C, or a parallel combination of L and C, and that gives different filters, notch filters, etc., stop band filters, which is sometimes called notch filter. That thing, that design is you can easily do, but all these at low frequency is okay, RF frequency is okay, up to 1 gigahertz, I say 1-2 gigahertz it is okay, but above that if you go, you see this will pose a serious problem. You need to have impedance matching M sections for that, etc., which creates lot of problem. We won't go into that. We will see that instead of this you can simply do it if you consider insertion loss, because whatever we say ideal filters in pass band, it should not have loss, but always it will have loss. If we calculate that loss and enforce that in pass band I need insertion loss to be within this, and in stop band I need it to be enormously high compared to pass band, that is a filter. So, in power terms we are saying that, here we are saying that in terms of propagation constant, that propagation constant should be lossless, that means attenuation constant should be 0. So, instead of that I can say that in terms of power, that insertion power. So, we will have to define what is insertion loss, that means in power terms what is the loss happening if I introduce this filter, and that if we can keep insertion loss to a minimum over a band, that will be pass band and very high at other bands. So, we can do microwave filter design by that, even all low frequency filters you can design by that. So, that is a more modern technique, and then you can have various functions to specify your stop band and pass band. So, any arbitrary specification you can make and you can synthesize a filter that is a huge story of research. Still it is evolving, that various specifications, because when you go to space, when you go for various modern electronic equipments, you have a plethora of specifications of filters. I want this to be cut to this much, I want that nearby it should have this specifications. So, various shapes are available, and you know, if you know how to do by insertion loss, you can incorporate all these things. We will see some typical cases, some Chevy shape, Butterworth, etc. shapes, which or various elliptic shapes, that how people do design filters from that insertion point from the next class. So, this more or less classes completes the low frequency part or RF part of the filter design. Microwave, which starts from roughly 1-2 gigahertz and mandatory for above 3 gigahertz, you cannot have this design because of this problem. Also your TEM mode, apart from that other mode starts propagating there, TEM modes, etc. And also you cannot consider that your distributed line is considering, as I said, TEM OM, other waves will start coming. So, you need to consider real wave picture. voltage and current doesn't have any meaning there. In equivalent sense, you can have voltage, current, but microwave things are based on electric field and magnetic field, etc. So, filter design there will be very complicated if we transform this network theory concept, voltage current concepts, but as I said, in terms of insertion loss, it will be very easy. Also, we will see that that makes the whole thing very computer program friendly, and by that nowadays all modern designs are insertion loss based. Thank you.